Most software running our world today sits dormant until a user clicks a button. The code remains inert until a human pushes data. Many developers apply this same logic to large language models. They treat the LLM as a stateless function, where a prompt triggers a text output, essentially a highly articulate search engine. An AI agent operates under a different set of mechanics. It requires an architecture capable of holding a persistent goal, accessing external tools, and looping through feedback until it achieves an objective. This split screen highlights the distinction. On the left, a standard chat interface provides a static answer. On the right, a Claude agent receives a goal, initiates parallel processes to research the problem, reads error logs, and delivers compiled code. Converting a model into an agent requires rigorous software engineering rather than clever prompting tricks. Anthropic designed Claude around a specific philosophy, the minimal footprint principle. During autonomous execution, this principle requires the agent to request only the permissions necessary for the task, while avoiding the storage of sensitive information beyond the immediate operation. While standard models focus on task completion, Claude is optimized to complete tasks under strict trust constraints. It is trained to pause and check with a human, rather than making assumptions in high-stakes environments. Deploying a production-ready agent requires building 4 discrete architectural layers on top of a probabilistic language model. We begin with the foundation. This is the base model. Locking in beneath it is layer 1, the system prompt. This invisible instruction set establishes the agent's baseline parameters before any user interaction begins. Standard models often follow system instructions with a dangerous literalism, executing exactly what is written, regardless of the broader context or potential consequences. Anthropic's training process focuses on intent over literalism. Claude is taught to recognize the spirit of the instructions rather than just the literal text. Consider an agent acting as a customer service representative. If a user presents a critical issue that technically falls outside the bot's predefined scope, a strictly literal model would simply reject the request. Claude utilizes its training to recognize when a literal interpretation would be unhelpful or harmful, allowing it to pause execution or seek human guidance. Aligning an agent with human intent provides the first line of defense against the risks of blind execution in live environments. Layer 2 introduces tool definitions, represented here by the nodes connecting to the model. These tools are frequently misunderstood as pre-programmed buttons or simple scripts within a user interface. Technically, these are JSON schema tooling, structured API descriptions that the model must evaluate to interact with the outside world. When facing a task, the model reasons about tool selection, constructs the necessary input variables, and interprets the resulting data to decide its next move. Data from the 2025 AI Safety Institute shows the impact of this reasoning. On complex computer tasks, the nearest competitor achieved a 71% success rate, while Claude reached 87%. This 16-point gap represents a significant reliability threshold for enterprise deployments. This performance difference is most apparent in computer use tasks, where an agent must visually interpret a screen and precisely control a mouse and keyboard to complete a multi-step workflow. A success rate of 87% moves the technology out of the realm of experimental demos and into the category of reliable production software. We complete the stack by adding the final layers: Layer 3, Retrieval Augmented Generation, and Layer 4, Memory. Claude manages context through 3 distinct memory types. In-context memory handles the active, precise state of the current conversation. This memory is fast and highly accurate, but it is limited by token length constraints. It cannot hold a company's entire data library at once. External memory solves this by using vector databases accessed via RAG, providing the agent with specialized knowledge on demand. Procedural memory consists of the logic and behavioral patterns established during the model's initial training. This procedural layer forms the foundation of the agent's judgment, dictating how it interprets information and interacts with users. Episodic memory is projected to arrive by mid-2026, which will enable agents to recall specific past interactions across different sessions. Treating memory state management as an afterthought is the most common reason for failure in serious AI development. Scaling an agentic system involves moving from a single stack to a multi-agent topology. A central orchestrator connects to multiple specialized worker nodes. The orchestrator receives a high-level goal and breaks it down into discrete subtasks. The worker nodes execute those subtasks using specific tools and return structured data to the central hub. This structure introduces a vulnerability. A worker might retrieve a malicious prompt injection from an external source and pass it back to the hub. Software engineers frequently assume that internal microservices operate within a trusted environment, meaning they might blindly trust data coming from a worker node. Claude's architecture employs a zero-trust orchestration defense to address this. As the data returns, the Claude orchestrator evaluates the worker's output for safety. If it detects a malicious payload, it stops execution before the data can reach the main line. Because Claude is trained to express uncertainty, the orchestrator can flag suspicious data and escalate the decision to a human supervisor. Internal skepticism is a mandatory architectural requirement for any system processing untrusted data sources. These theoretical architectures are already delivering results. One healthcare system deployed a Claude multi-agent pipeline to process prior authorizations. The system interpreted unstructured clinical data and checked it against insurance policies, resulting in a 70% reduction in processing time. Agentic scaling laws govern these deployments. This graph shows performance versus model size and compute. For simple questions, small models plateau early, performing almost as well as frontier models. However, for complex multi-step workflows, performance scales linearly only when using the most capable models. Utilizing a low-capability model at the orchestration layer often results in reasoning failures that degrade the entire multi-agent pipeline. Cutting compute costs at the hub of an agentic system fundamentally breaks the value of the multi-agent approach. As these networks grow, we are seeing the rise of unexpected behaviors. Research from the University of Toronto recently documented this trend. They identified emergent norms, instances where multi-agent systems developed their own communication conventions and ways of dividing labor. These patterns emerged naturally through agent interactions, without any explicit instructions and the original prompts. We are witnessing systems that autonomously organize and optimize their own internal logic at scale. Within 5 years, agentic skills will likely become the underlying infrastructure of the internet rather than a separate product category. This mirrors the transition of the early 2000s, where companies that mastered web protocols early gained a decisive advantage for the following decades. While specific models will evolve, mastering the engineering behind memory, tool use, and multi-agent orchestration is the only way to build leverage for the next era of software.